All right, welcome to Calculus. I did have to redo the lecture notes because couldn't use my computer during class. So here it is. Here's the lecture notes after class. We are at 3.6. We're doing something called the chain rule. And this isn't just a technique that you use. It's called a rule, but it's a technique that you use when you get more complicated derivatives. So let's actually just start. I want you guys to try it. That's what I want you guys to do. I want you to try this and see if you could do it the long way. But example, we're going to take the derivative of sine 3x. All right, so I think you know what that is. And you should probably think about the fact that, I think it's a product rule with 3 of them in there. So we're actually going to use product rule. So when you do this, set it up as, let's see, I'm going to take the derivative of the sine of x multiplied by sine of x multiplied by sine of x. Okay, again, we're kind of just giving an example of, we're deriving the chain rule of a specific problem. That's what we're doing. So how would you do this? How would you take the derivative of sine of x times sine of x times sine of x? All right, I think what we would normally do is we take the derivative of the first. Let's see if we put up our little rule here. If we have 3 different functions, we're going to call it f gh. We're going to take the derivative of that. And so what happens here, you take the derivative of the first one and you multiply times the other 2, add. Then you take the derivative of the second one and you multiply with the other 2. And then you take the derivative of the third one and you multiply it times the other 2. So we're going to do exactly the same thing here. So as we do this, we're developing the chain rule. Here it is. So the derivative of the first one, sine of x, is going to give us cosine. But notice the other 2 are going to remain the same. So in this case, it's just going to be sine squared x. And then as we get to this one, then we're going to take the derivative of the second one, which becomes cosine of x. And then the other 2 will just be sine remaining, sine x times sine x. So we get sine squared x. Okay. Then the third one, same thing. We're going to take the derivative of this last one here, call it cosine of x. So then you still have this sine squared x on your hands. So what did we get? We got this whole concept of, looks like there's 3 of them, right? 3. And normally whenever we write sine and cosine, we write the sine first. And there it is. Okay, we've got the derivative of this. And now the question is, how can we go from the derivative directly to here? Is there a process that we can use? And before we started this in class, I did ask the class, what do you think the derivative should be? And there was an answer in the class saying that the derivative should be something like this, which is pretty close, right? Notice you're taking the power rule and then you're taking the this derivative of sine, and so that's not it, but then this is. So we're going to take a little guess as to what we do. So it looks like we take the power rule. In fact, let's kind of set this up so we know what we're talking about nicely here. This is the other way to write it, right? So notice what happened here. It looks like we took the power rule, we put the 3 in front, we subtracted 1 from it, gave us the 2, and then we left that sine of x just nicely still inside there. And then what we did is we took the derivative of the sine curve. So let's see if this makes sense. You take the derivative of the outside function. In this case, it was the power rule of x cubed. And then you leave everything else inside there exactly the same. And then you take the derivative of the inside stuff. Okay, so that's kind of what you should sort of see. Like, hey, I think it works that way. Okay, let's do this here. Let's see if this works the same way on another problem. Again, we're just deriving the chain rule. We're looking at examples, seeing if it's going to fit our general of how we do calculus here. So let me do this here. Let me do a bracket here. Do parentheses and let's go 3x squared. Okay, all yours here. Can you do this one? Okay. And it's going to be, again, it's going to be 4 terms that are exactly the same, and you're going to use the product rule. All right, and you can fast forward this, you can stop it however you like to sort of try it yourself. That's fine too. So let's go with it here. So the way I would think about it first is I'm taking the derivative of 4 things that are exactly the same. So 1, 2, 3, and 4. This is going to be a long problem, but needed for us to understand this. So again, same thing here. If we have a product rule on our hands, what we're going to do is we're going to take the derivative of the first one, right, and then leave all the other ones exactly the same. And let's see if our our hunch works here. So the derivative of the first one would be 6x, and then we're going to have 3 of the remaining things here. So 3x squared plus 1 cubed. Okay, that's nice. Then we're going to have another one, right? Now we're taking the derivative of the second one, leaving the first one the same. So we're going to take the derivative of this guy, leaves us with 6x times 3x squared plus 1 to the third. Okay, and then we're going to do this again. So 6x is the derivative inside the parenthesis. Oh, I'm actually saying the chain rule here. No, this is just the derivative of the third one and the derivative of the fourth one. 6x, 3x squared plus 1 to the third. Okay, I think we got it here. Let's simplify this here. So it looks like I have 4 of these. So let's put 4. And just to make it look a little bit better and for us to realize what the chain rule looks like, I'm going to write the 3x squared plus 1 to the third power. And then this little 6x that can be factored out of all of this. Okay, I think we got it. And so notice right here is your power rule. And notice the stuff inside the parenthesis remained the same. Then notice that you took the derivative of the stuff inside. Okay, so then let's go on. Okay, so let me give you the chain rule and see if you agree. So the chain rule is this. So first of all, we have to have a function that's inside another function. And do you guys remember for all the way from algebra 2, you had this little guy like this. You had f(h) of x is if you have one function that's over another function. So notice this f is the outside function, g is the inside function. All right, if you guys remember back to algebra, I think we, this is called the composition of functions. We had a specific notation for it. It was like this. It was like an open dot, like that. So hopefully you guys remember algebra 2, at least a little bit. So there it is. So this just means that g is our inside function. F is our outside function. So if I have that, we just go into the next one here. So the derivative would be, we take the derivative of the outside function and we leave the inside function exactly the same, no change. And then what we do is we take the derivative of the inside function. All right, there was a famous movie here about a math teacher by the name of Jaime Escalante. He came and he started teaching math, and he started developing an AP calculus class. Do you guys remember that? I don't know if you guys seen it here sometime here, but he was talking about when he was talking about this, he was talking about what we do is we just peel an onion. This is a math teacher watching a math movie, right? So you have onion, you have all these different layers in an onion, right? And so what you do is you just peel away the top layer goes first, then you peel away to the second layer, third layer, so forth. That's exactly how the chain rule works. All right, the other notation, which we should introduce the notation, we'll actually work with it later. Not today, but the next day. So there's another way to do it. It says if you're trying to take the derivative of y with respect to x, You take the derivative of y with respect to u, and then you take the u with respect to x. So notice we kind of put this little intermediary term in here. Okay, so we'll take a look at this one a little bit later. That's called Leibniz notation, but we're going to concentrate on just this little piece right here. So in fact, we're just going to do a whole bunch of derivatives. That's what we're going to do right now. So all yours, let's go. So this will be exercise 1. Find the derivative. All right. And as I set this up, let me just take a look at one little thing real quickly here. All right, find the derivative of, I should say of. Okay, let's go for it. Let's start here. So find the derivative of sine cube x. Hey, we already done that before. So as far as notation goes, what I don't want you to do as students, I don't want you to put an equal sign here and then start taking derivative of stuff. Don't do that because that's not the same. So if you want to show that you're taking derivative of something, so the directions are find the derivative of, so you're going to say, okay, so the derivative of sine cubed x will be, and now let's talk about this here. So we're going to take the derivative of the outside function and then coming into it. So the outside function, if you kind of think about it, is just this little concept of x cubed, right? It's a power function. Then the inside function, so if you kind of want to do it the way, separate them out if you want to, then you have sort of like this. There's your two functions. You have a function that's cubing something, that little 3 there. Then you have a function that's taking the sine value of something. So in order to take the derivative of that, in fact, we can probably even do it like this. This would just be an easier way of seeing it. We have sine of x to the 3rd power. So outside function, right? Inside function. Outside the parenthesis, inside the parenthesis. So let's go for it here. So as we do this here, we are going to take the derivative of x to the 3rd, or something cubed. The derivative is 3 squared here, and whatever's inside is exactly the same, has not changed. Then what we do is we multiply it by the derivative of whatever's inside. And that would be, let's see, derivative of sine is cosine. And we are done. That is it. Hey, is that what we got initially on our previous? Yeah, just kind of, if you want to write it nicely, you can write it like that. There it is. 3 sine squared x times cosine x, which is exactly what we got on the previous slide when we did the derivative of that. Perfecto. Okay, you know what number 2 is all about, or B. Take the derivative of 3x squared plus 1 to the 4th. All yours. Give you a little bit of time. All right, you can pause this if you like to go a little faster, or for you to try it yourself here. So let me put all this good stuff in. All right, outside function. What is it? It is something to the 4th power, right? So we're going to take derivative of taking something to the 4th power. 4 goes out in front. The inside stays exactly the same, no change whatsoever. And then we subtract 1 from the exponent. Then we take the derivative of the stuff that's inside. So derivative of, maybe off to the side if you need to, you can do it off to the side. You can kind of go like this here. Boom, that would be 6x. And so bring it down, multiplied by 6x. And then yes, you do have to simplify this. The sine and the cosine could not be simplified, so it stayed this way, but that 4 and that 6x could be multiplied together. So we are going to go with 24x, 3x squared plus 1 to the 3rd. Done. Okay, now we're going to go for quite a while, all right, with this. So I'm going to give you a problem. This is pretty much for the rest of the time here. I'm going to give you a problem. Try it yourself first, turn on the video, and see if you guys got the same answer as I did. All right, so let's go through each of these here. All right, Can you take the derivative of something looks like this? All right, so notice this is it's going to be a chain rule because what you see in your denominator over there. But also it's going to be a quotient rule. So yes, now we're mixing those rules together. And so let's go with it here. So the derivative of all this, I should put brackets again to distinguish my groupings. Boom, boom, boom. Okay, I think we're ready to go. Yeah, let's go with it here. So what calculus students tend to do is they'll just write out the rules ahead of time so they know exactly what they're going to do. So this is a quotient rule I'm going to deal with here. So f divided by g, and I'm going to take a derivative of it, which means the derivative of the first times the second minus derivative of the second times the first all over the second squared. We're good? Really don't need those parentheses there. I guess we could just write g squared. Okay, that's the quotient rule. That's what we learned from previous lessons here. So we're going to implement that. So our top function is 1. So technically the derivative of it is 0. That's nice. That's there. And then multiplied by 3x squared plus 1 to the second power. That's cool. Minus sign goes down. Now the fun begins. Can you take the derivative of 3x squared plus 1 to the second power? Now you may want to have to do it off to the side as well. If you need to do it off to the side, just to do it. It's going to be 3x squared plus 1 squared. If you do it inside the problem, it becomes really cumbersome to sort of see all the stuff. And so if I do that, it's going to be, let's see, 2 goes on the outside. Inside stays exactly the same. Now it's to the 1 power, and then you multiply it by the 6x. Perfect. So all yours. Can you simplify that? All right, give you maybe 20 seconds to try to do it yourself. Go a little bit ahead of me. All right, that was good enough. Okay, let's go. So the derivative of this would be, let's see, let's try to put it together here. So 2 times 6x is 12x. Good there for that. 3x squared plus 1. All that divided by the g function, or our denominator function, and then that to the second power. So we'll do something like that. Okay, we're almost done. Let's go with it. So this is multiplies by 0. That's crossed out. That goes away. And I'm left with a negative 12x, left with a 3x squared plus 1 on top. And I'm left with 3x squared plus 1 to the 4th power. And yes, you do have to simplify as much as you can. So in this case, that goes away with one of these. So now left with 3 of those. So final answer, negative 12x all over 3x squared plus 1 to the 3rd power. Voila, you have just done the derivative of a quotient, including a chain rule inside it. Whew, awesome, congratulations. Okay, so let's try some. And again, do it yourself first if you have confidence in it, and then check to see the video to see if we're both okay. D. Can you take the derivative of cosine of 5x squared? All yours. Take a little bit of time to do it. Pause the video if you need to. All right, now I'm going to try it as well here. So let's see the derivative of cosine of 5x squared. Okay, so a question came up in class. Is this kind of different than what we did before? Yes, because the cosine is actually now the outside function, and the 5x squared is now the inside function. So that's all the difference there. So let's go with it. The outside function is cosine. The derivative of that would be sine, and you keep everything else exactly the same. All right, then you multiply it times the derivative of the inside function. Derivative of 5x squared is going to be 10x, and voila, we are done. It is 10x sine of 5x squared. Perfect. Love it. Awesome. Okay, next one. E, okay, all yours. Secant of 4x to the 5th plus 2x. So all yours, have fun. Again, give you guys a little bit of time to get started with it. All right, so the derivative of secant. This is going to be fun. It's always fun, though. So look up derivative of secant if you don't know what it is off the top of your head. How could it possibly be you don't know what it is on the top of your head? Oof, okay. Let's go with it here. So the derivative of secant is secant x tangent x. So again, this is an inside function. So this is going to remain exactly the same. So it's secant of that, tangent of that. Then all of that multiplied by, I'll put a little dot there, the derivative of 4x to the 5th plus 2x, which is 20x to the 4th. Was that plus 2, I guess, right? Okay, how do we write it? We usually like to write the coefficients, as we call them, in front of trig functions here. So in this case, we would just move this little 20x to the 5th plus 2 out in front, and then everything else follows exactly as is. Okay, so there's our secant derivative. That's cool. Okay, so again, peel the onion. Look what is the outside function, what is the inside function, and then you go from there. So let's change it up just a little bit here. So far, we've been integrating chain rule into things here. So how about this? This is E, so this is F. All right, can you take the derivative of all right, there is that. So again, take some time, pause the video if you need to here to do that, and we go from there. All right, so notice technically you have two chain rules going to happen, and this is sitting inside a product rule. So, whew, gets a little more complicated here. So I think we're going to go with it here. So the derivative of that times that. Okay, so if you need to, so here's just a few tricks of the trade. How about that? First things first, if you're not sure the way you're going to go and not sure of all the pieces here, let's write down the product rule. So we have that in front of our face here. So fg prime would make f prime of g, right? Derivative of the first times the second times the derivative of the second times the first. Okay, that's one piece there. Also, if the derivative itself gets a little bit more complicated, and this is again, sweet little trick of the trade, you can go over here and off to the side before you even start the problem. What you can do is you can take the derivative already, and then you can just start plugging stuff in only. It makes it a whole bunch easier than trying to do all the simplification inside the problem itself. So I'm going to take the derivative of my first function. So this right here, that's my first function, because I know I'm going to take the derivative of it anyways here. So derivative would be 5. Then it'd be what? 2x plus 1 to the 4th times 2. So in simplified form, this is 10, 2x plus 1 to the 4th. Okay, let's take the derivative of the second function. Again, you should see it as like, oh, that's so much more easier than trying to simplify stuff inside the function. Derivative of that guy, 7 in front because the power rule, 3x minus 2 to the 6th power, and then you multiply that times the derivative here. So 3x minus 2, derivative would just be 3. Simplified form is 21. 3x minus 2 to the 6th. Now we're ready to begin our problem, and very easily. So we'll go with the derivative of our first function, 10, let's see, 2x plus 1 to the 4th. Cool. There's that times the original g function. No changes to g, no changes to the second function. That just comes over from over here. Plus sign goes down. Oh, erase my g. And then now we can take the derivative of our second function. So now it's 21, 3x minus 2 to the sixth. Boom. Times the original f function. So 2x minus, or sorry, plus 1 to the fifth. Let me make that parenthesis a little bit better. Okay, perfect. Now the question is, Mr. Hanjiev, do you have to simplify this? Yes, you do. Bummer. Yes, you do. With the trig functions, usually they're a lot more easier, right? Because they're just secant of something, tangent of something with the coefficient in front, and that's it. With these guys, there's a little bit more work here. So let's try it. Let's go for it here. All right, so just like factoring out stuff here, I'm going to go change my pen color here first. All right, I'm thinking 10 and 21, they have nothing in common, so there's nothing to pull out there. Next is these guys here. So this little 2x plus 1, I have 4 of them in front. I have 2x plus 1, 5 of them in the back. So that means I get to pull out 2x plus 1 to the fourth. Remember, in factoring, we always take out the lowest exponent. Okay, we'll see what that happens there. Then we got to do the other one here. So 3x minus 2 parenthesis, that factor and that factor. Take out the lowest exponent, makes us 3x minus 2 to the sixth power. Okay, the question is, what's left over? What's left over inside here? Well, let's see, the 10 was left over from our first form. We took the whole entire 2x plus 1 out completely, so we do have an extra 3x minus 2 here, plus sign. 21 stayed in our second term. And we factored 4 of the stuff at the end, but there's 5 of them, so we have an extra 2x plus 1. So let's simplify that down, and we're going to call it good after that. Okay, so this would be, let's see, 30x minus 20, looks like, plus 42x plus 21. I like that. And I think we are almost done. Let's see, I got myself a 72x plus 1. There it is. And then can I factor anything else out, or is that about it? Yeah, that's about it. There's nothing else to factor out. Okay, so there it is. That's probably one of the more complicated ones that you've done here. So that's the product rule. Let's do a little bit more difficult chain rule. I'm sorry, quotient rule. Not by much, but just a little tiny bit more difficult. So let you guys try it before you guys get through the homework here. So we are on F, so this is G. All right, taking the derivative of this. Oh, you know what we could do? Actually put plus 5 there, and this would be 2x plus 3 to the third power. Okay, so x plus 5 on top, 2x plus 3 to the third power on the bottom. Let's see how this will work out. All right, if you want to try yourself first, go for it. If you want to follow me, let's do it together here. So first things first, I notice this is a quotient rule. So off to the side, I'm thinking to myself, whoa, that skipped back. I'm thinking to myself this, F divided by G prime would give me F prime G minus G prime F over G squared. Da, 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 da. That's one thing. Okay, now the other one is, remember how we did before? We did the derivatives ahead of time. Let's just make it easier on us here. So let's do that here. So it's the derivative of the top. So derivative of x plus 5 will just be a 1. That's cool. That's the top. Now we got derivative of the bottom. So the derivative here would be Let me actually put it, no, yeah, that's fine. 3 here, 2x plus 3, the second power times 2. So simplified form, this is just 6, 2x plus 3 to the second power. Dun, da, da, da. Okay. I think we're ready for the derivative here. Let's go with it here. So the derivative of this function or expression is going to be the derivative of the top times the bottom, original function, minus sign, the derivative of the bottom times the top function divided by the derivative, or sorry, just the bottom squared. Boom, there it is. Okay, now let's start simplifying. Yes, we got to simplify. Okay, looks like the 2x plus 3 to the second power is going to get out of there. I'm putting a bracket just in case it gets more complicated. So 2x plus 3 to the second, because it's the lowest exponent is here between these guys. Then I don't see anything else in common. So in that case, I do that. So for the first term, this piece here, I'm left with a 2x plus 3, an extra one. We got rid of all those. So then I'm left with a negative 6 that's being multiplied to x plus 5. All right. Okay, and the rest of it is just algebra. You will notice that in calculus, the calculus part is actually pretty easy. It's the algebra stuff that's going to throw you off most of the time, because just so much simplification and so much little hoops to go through. All right, I think we're almost done. Let's go with it here. So 2x minus 6x makes negative 4x. Da, da, da. And then we got a 3 minus 30 makes negative 27. Okay, there it is. Final answer. That's great. All right, well, let me give you a little bit of news here. So far, what we've been doing is two-stage chain rule, right? You have an outside function, and then you have an inside function. So first function, second function. Let's get a little bit more ingenious. Let's go to a 3-stage. So 3 onion peels. How about that? Can you take a derivative of this? Cosine to the 4th power of 7x squared plus 1. Whew, all yours there. So if you want to, you can kind of think about what are the different functions you have. It may be even easier to write it out like this. Right there. So the inside function is cosine of 7x squared plus 1, but then it's to the 4th power. So let's see if this makes sense here. So I got a first function, which is the 4th power. That's my first function to deal with. Then I have a second function, which is right over here. The second function is the cosine, and then I also have a third function. So now we go 3 layers deep. That's what we want to do right there. So we're going to take the derivative of the first function, leave everything else the same. We're going to take the derivative of cosine, leave everything else the same, and then we're going to take derivative of the inside function, leave everything else the same. So let's go with it here. So derivative of all of this. All right, if you want to, you can write it the other way as well. If you want to, you can write it as that. Ooh, this is going to get kind of looking crazy here because you have a double. So again, if you can kind of get away with not doing that, it just gets super, super complicated. And so you don't want to get too complicated with that here. So just notice this is the exponent on the cosine. We're going to deal with that first. We're going to deal with the cosine second. And we're going to deal with the stuff inside there third. Let's go with it here. So power rule says 4 goes out in front. everything else inside here remains the same. And what we do is we subtract 1 from the exponent. So 4 goes down to 3. Everything else remained the same. Next on the list now is the cosine issue. So cosine, let's see, the derivative of cosine is negative sine. And then again, everything else inside that parenthesis remains exactly the same. And then we're going to take the derivative of the stuff inside the parenthesis. So the 7x squared plus 1, that it changes into a 14x. Whew, that was kind of a bit of a toughie there. I think you guys hopefully handled it pretty well there. So again, here was the derivative of the 4th power. Here was the derivative of cosine of x changing into sine of x. And here was the derivative of 7x squared plus 1, all those little pieces that are in here. Okay, but let's put this together now. Simplifying it all out by multiplication, I have a negative sign that's right here. So I got a negative 4 times 14 is 56. I have an x that came from the 14. And whenever we write trig functions, it's not wrong, but customarily what we do is we just usually write the sine value first, or the sine trig function first. If it's a choice between sine and cosine or sine and any other ones, we usually like to write them in some kind of order. So, not that if you wrote the cosine first, it would be a mistake. You wouldn't, just customary. There it is, guys. That was it. This one and the previous one was pretty big stuff. But if you're handling this, you're doing great. Okay, how about one for you to try? A little bit less complicated, but I at least want you guys to try. So take this one here, very similar. All yours. So sine to the 6th power x cubed, or sine of x cubed to the 6th power. All right, I'm going to try it as well here. So off to the side over here. All right, I'm going to go with it here. So first things first is deal with the 6th power. 6 goes in front. Sine now becomes to the 5th power, and the stuff inside remains exactly the same. Multiplied by the derivative of sine is cosine of the stuff that's inside exactly stays the same. And now the derivative of the stuff inside, which is 3x squared. Perfect. Okay, so out of this becomes, let's see, 3 times 8 is 18. I got myself an x squared that comes in as well, and I got myself my trig sine function and my trig cosine function. That is it. Done. And one more problem to go. So let's go with it here. Ooh, you know what? Now we reached exercise number 2. All this time. So here's exercise number 2. Find the equation of the tangent line. So let me just check here. I wonder if tangent line is supposed to be. So you can start writing it already here. So find the derivative, find the equation of the tangent line of the graph, actually I should say, of the graph h of x is equal to, ooh, how fun is that? I think we should recognize that. That should be a 5 there. It should be minus. And then I'm going to say at, let me write it here, at x is equal to 2. Stop there. Okay, so let's go back to what we've learned in algebra real quickly here. Do you guys remember finding the equation of a line? Any kind of line. Let's kind of do that first. So if you say, hey, find the equation of a line, in your mind you should have this equation right away. So if you're trying to find the equation of a line, anytime. There it is. It's the point slope form. Find the equation of a line. And in algebra, algebra 1, algebra 2, I think we just said find the equation of a line that passes through, let me just kind of do this here, like 5, 2 with a slope of 3. Who do you guys remember that? And what you had to do in algebra 1 is you just plugged in your points. Their slope came in as 3, your y value came in as 5, and your x1 value came in as 2, and you did it. And then algebra 2, you guys got a little more sophisticated. And then what the teacher says is find an equation of a line that passes through 2, 5, and 4, 12. And so that changed a little bit here. So you could no longer do that. You could no longer just plug stuff in right away. But you had this extra little formula that said, hey, you know what? I can still get the equation of slope just by subtracting my y values, subtracting my x values, and voila. And then you could still plug in your m, and then you get to choose. You want to choose the 2, 5 or the 12, 4, or the 4, 12. You got a choice that you could make, and you did it like that, and then you go from there. Okay, so now we're moving on. That was the two sort of algebra problems that led to this one here. Now we're here. So the only change is we're dealing with functions. The coordinates are not given right away, and you're trying to figure out the tangent line. So then this guy, that little slope, has to be the derivative. Okay, next is you actually know what in the numbers already because it gives you. Specifically, you want to know when is this tangent line when x is equal to 2. Okay, so let me do this here. Let me draw this kind of sort of. And if you want to draw it on your calculator, that's fine too. We have a vertical tangent line, a vertical asymptote right here. I'm just kind of drawing it from what I know about graphs. Boom. Boom. That's probably what it looks like on your calculator. What we have is we have this little point right here. That's what we're trying to find. So we're trying to find the tangent line to that point. It's the line that's going to go just barely nick this and keep on going. That's what we're trying to find right there. In fact, let me do this here. I'm going to change my pin color just so we have it as the important line right here. It's the line that is going to go and hit just barely that and keeps on going right there. Oof. Okay, let me draw it so it's actually one complete line. Okay, is that better? That's better. Okay, that's perfect. Okay, so what do we need? We're missing the derivative at that point. So notice that it's not everywhere, right? It's actually just at a specific point. We're missing this y value. So how do we get this y value? Well, if I know what the x value is, I got to plug this stuff in and get the y value. So the y value is just the original function at 2. So let's do that. Let's do that real quickly here. If I plug in a 2 into my function, that'd be 3 times 2 minus 5 squared, which becomes 6 minus 5, which is 1, 1 squared, and 1 over 1 is 1, and we get ourselves a 1. That's perfect. Okay, so I can start my formula now. Y minus 1 is equal to, oh, I don't know what that is yet, but I can go x minus 2 because that was given already here. So now let's go find technically the slope at that particular point. How do we find the slope? We take the derivative. All right, taking the derivative, this is a quotient rule. So the derivative of the top times the bottom minus the derivative of the bottom. So let's see how we could do this in our minds here. This is going to be 2. Inside stays the same. That becomes a 1 there. And then we multiply it times the derivative of the inside function multiplied by the top function. Divide by that guy being squared. Okay. Perfect. Okay, so this goes away. No need for that. This becomes a negative 6. Let's see, 3x minus 5 on top. I think I'm doing this right. To the 4th power. Okay, and then we can cross out one of these, cross out one of those to become a 3, and I got myself a negative 6 over 3x minus 5 to the third power. Okay, again, that was just the derivative, right? But what we want is we want the slope line at that particular point. So all we got to do, just one little thing here, is plug a 2 into our derivative. We have the equation. Now let's plug in the 2. All right, what do you got? Here's negative 6. I got myself a 3 times 2 minus 5 to the third. So notice this equation is not the original one, right? I'm not plugging into the original to find the y. We're plugging into our derivative to find the m. And let's see what we got here. We got 6 minus 5 is 1. 1 to the third power is 1. And negative 6 over 1 is just still negative 6. Dun, da, da, da. Okay, that is what we have here. So it looks like a football game over here. But that should go right there. Boom. We do have to simplify it. So time remaining, let's go. It's y minus 1 equal to negative 6. And it's x minus 2 on the next slide. Let's finish this off. So distribute the negative 6 over. We got ourselves negative 6x plus 12 looks like. Yep. And then we add one more in there, and we get ourselves a negative 6x plus 13. There's our equation of our tangent line that hits our graph exactly at the point that we want. Okay, let's go back. So there it is. We figured out this equation of this line becoming negative 6x plus 13, which is kind of looks like it, right? Because you have to go all the way up here. Looks like it hits at 13. And the slope of this line is negative 6 all the way down. Neat. Well, again, we'll be doing some other stuff with this later on. But that is the end of the lecture for today. Hopefully you got it. And then again, email me if you have any questions on it. Have a good day.